Hey everyone, welcome back to MP Coding. I'm stoked you're here for what feels like the real kickoff, our very first kernel module. Today, we're building a super simple Hello World driver that'll print right into the kernel's debug console, and along the way, I'll break down the key commands, what they do under the hood in kernel space, and why they matter. No fluff, just hands-on steps you can follow in VS Code on your Pi. If you haven't set up from the last video, Raspberry Pi OS, SSH, VS Code with that C++ pack, and our LDD folder, please watch that video first, because we're jumping straight in. Quick recap. Last time, we got the Pi booted, SSH'd in, hooked up VS Code remotely, installed those extensions for Smart C editing, and backed up the kernel build dir. Now, inside our LDD folder, I have created this subfolder called First Kernel Module to keep things organized. Now I'm creating a other folder inside this folder. I'll name it like 01_hello, so they line up with our series roadmap. Makes it easy to track progress. This whole thing's inspired by the classic Hello World example in the Linux Device Drivers book, 3rd edition. Grab it if you haven't, it's gold. That sample shows the bare bones, code, build, insert. I'll walk us through it, explaining each piece as we go, and tweak it just a tad for clarity on the Pi. First up, we need two files, the source code, hello.c, and a makefile to handle the build magic without typing a novel each time. Let's knock out the makefile. Starting with the top, obj-m plus equals hello.o. This is the linchpin that tells the kernel's build system exactly what we're up to. obj-m is a special variable baked into the kernel's kbuild system. Think of it as the flag that screams, hey, I'm building a loadable module, not some permanent chunk of the kernel itself. The -m stands for module, so obj-m lists the object files that get compiled into standalone .ko files you can ins-mod later. Now, the plus equals part, that's just a handy shorthand and makes syntax. The equals sign assigns the value, but the plus equals appends to whatever's already there, adds hello.o to the object module list without wiping out any previous entries. Why append? In bigger projects, you might have multiple modules in one directory, so this lets you stack them up. Next, the all target. That's the default goal when you just run make. Here I'm not going to explain about makefile. Please search about in the internet. Type all, then hit enter to drop to a new line. Here we need to give tab character, not spaces. Tabs signal the command to run. Spaces will just confuse it and throw errors, so make sure to give a tab. Then type make space -C, which changes directory straight to your kernel's build folder. Then /lib/modules/ $sign shell space you name -r. That dynamically pulls your running kernel version, like 6.1 whatever. Follow it with /build. That's the heart of the kernel sources and headers. Next, space M equals $pwd. This tells the builder, hey, my module files are right here in the current working directory, so it doesn't go scavenging elsewhere. Finally, space modules. That kicks off the whole build chain, compiles your C code, links it against kernel bits, and pops out the .ko file, your shiny loadable module. And after that, for cleaning up the module, say, to wipe out those temporary build files and start fresh, we've got the clean target right below. It's basically the same command as in all, but swap out that final modules for clean. That calls the kernel's cleanup rules in the same build dir, nuking.o files, any leftover objects, and junk from botched compiles. Keeps your workspace spotless and builds repeatable every time. That's it for the makefile, folks. Short, sweet, and set to automate the heavy lifting. Save file, and let's pivot to the real star, our hello.c file, where the code comes alive. Alright, first things first, in our hello.c, we gotta pull in those essential Linux header files to make the magic happen. So, type include linux/module.h. That's the core for all module registration stuff, like init and exit hooks. Then, right below it, include linux/init.h. And look at that. As soon as I start typing linux/, VS Code's IntelliSense kicks in with a drop-down of suggestions, spotting module.h and init.h right away. That's the beauty of that C/C++ extension pack we installed, paired with our C++ properties.json. Config pointing to the kernel includes. It saves so much guesswork. No more fumbling through docs or wondering if you spelled it right. It's like having a kernel-savvy copilot, especially when we're scaling up to full-blown drivers with a dozen headers. Super game-changing for staying in the flow. Next up, We need to hook in our module's entry and exit points. These are the module_init and module_exit macros that basically whisper to the kernel. Init macro, we need to pass init function. Exit macro, we need to pass our exit function. Now let's sketch out our init function. This is the heart of the module, the very first thing the kernel calls when you load it with insmod. I'll name it my_init for clarity. It's a plain function that takes no parameters, and it returns an integer to signal how loading went. Here's the exit function, our cleanup crew that runs on remove module. No return value needed, since unloading doesn't fail. The kernel just yanks it if you're done. Okay, now pass these two functions to the init and exit module macro. Alright, let's actually build this thing and see it come to life. First, make sure you're in the right spot. cd into hello.c file directory. From there, it's as easy as typing make and hitting enter. That kicks off the whole automation we set up, pulling in the kernel headers, compiling our code, and linking it into that hello.ko file we can load. But hold up, it's choking with something like error. Missing module license. The Linux kernel's got this built-in paranoia about licensing. It demands every module declare its license up front with that module_license. Without it, the kernel assumes your code's proprietary or shady, and it flat out refuses to build or load it. So I will give GPL here. If you want to dive deeper into the licensing weeds, like what GPL means for your kernel tinkerings or the other options out there, hop on the internet and search it up. Tons of solid reads waiting for you. Let's hit make one more time now that we've got that GPL license stamped on. Watch it go. And there we go, building clean as a whistle, no errors in sight. If you peek into the folder here, you'll see a whole bunch of new files. The .o object from our compile, and right here hello.ko file. That's the loadable kernel object file, the actual module ready to plug into the Pi's kernel. Before we rush to load this, let's add some kernel prints so we can actually see it talking back when we load and unload. Here in the my_init function right before the return 0, add print k, type some message like hello kernel. Print k is output straight to the kernel's debug console. Then, in the my_exit function, print message like goodbye kernel. Alright, let's fire up that build one last time now that we've sprinkled in those print calls. Back in the terminal, just type make again and hit enter. Before we shove it into the kernel, let's take a quick peek at what's already living there. Gives us a baseline to spot our new guy. Type lsmod and hit enter. There's the list. All the modules currently loaded and humming in kernel space, like Bluetooth. I2C_dev for those sensor buses, IPv6 for network stacks, bunch of them. Each handling their slice of hardware or services. Yours might vary a bit depending on your Pi setup, but it's cool to see the kernel's ecosystem in action. Okay, time to join the party. Load our hello module with sudo insmod hello.ko. Hit enter. It takes that .ko file, ko standing for kernel object, basically a compact, relocatable blob of compiled code with all the symbols and deps resolved, and dynamically plugs it right into the running kernel without a reboot. Now if we look the dmessage log, type dmesg and hit enter, you can see the hello kernel message in bottom of the message console. Hey, quick note on those top two lines popping up in the output. They're just echoes from me loading and unloading the module during testing I did earlier. This is the one for this module load. Alright, let's run lsmod again. Scroll up a bit. There it is, right near the top, hello, in the module list. And currently no one using it. We nailed it. Our very first kernel module loaded up clean and cozy in the Pi's kernel space. Okay, let's remove the module. Type sudo rmmod hello. Here we can give either hello.ko or just hello. Both are valid. If we check lsmod again, you can see the hello module's been removed from the kernel list. In dmessages, you can see that goodbye message printed out right at the end. That means when we remove the kernel module with rmmod, my exit function gets called right away. Before we roll on to the next bit, let me quickly demo a few handy dmessage tricks. These will make spotting your module's chatter way easier than scrolling through a wall of text. So, if you just type dmessage, it'll dump the entire kernel message buffer right to the console. everything from boot logs to your latest prints. Now, crank it up with dmessage-W. That's the watch flag. It'll sit there and wait, printing out only new kernel messages as they hit, like a live tail or screen session. Watch this. I'll load and unload our hello module one more time with insmod and rmmod. You can see the new messages are print out in real time. Another quick one, dmessage vertical bar tail. That grabs just the end of the buffer, the most recent messages, skipping the old boot stuff. And if you want to dial it in, add a number like this. This now shows only the last 25 lines only. Now I have opened the new terminal and then set dmessage screening. Let me quickly load the module again. Let's run modinfo hello.ko. Hit enter, and there it is, the kernel module's info. Here, you can see the license name, version details, and all sorts of other metadata popping up. Pretty neat how modinfo lays it all out at a glance. If we take a quick peek at that auto-generated hello.mod.c file, yeah, the one make whipped up behind the scenes, you can see it's automatically cranking out some of metadata for our kernel module, like version stamps. Alright, let me show you how to add some other metadata to our hello module. With the module_author macro, we can slap on the author's name right there in the code. And just like that, you can see there's a whole bunch of these handy macros for setting metadata, super straightforward. I'll toss in one more right now. Module description for our hello module. Here I will give our first dynamically loadable kernel module. And one more thing we can toss in. These __init and __exit function declarations. They're nothing fancy, really, just a nice touch to flag to the compiler and linker that these routines are only called once at load or unload, so the kernel can optimize away the code after it's done with them. Keeps things efficient. Alright, let's build again. Load the module. Now, if we check the module info again with modinfo hello.ko, you can see all that new metadata showing up right there. The description, the author, everything we added, looking sharp and documented. Okay, remove the module. Then, run make clean to sweep away all those temporary build files, the .o objects. And that's a wrap for today's video. We kept things nice and straightforward, diving into the basics of kernel modules and actually loading up our simple hello one to watch it come alive. From sketching out the code and hitting that build, to insmod and rmmod, plus those satisfying dmessage outputs and some metadata. In next video, I'll walk you through kernel print levels. They're a game changer for debugging and fine-tuning your modules without the guesswork. Thanks for hanging out on MP Coding. Hit that like if you're pumped, subscribe so you don't miss the drop, and drop a comment. See you in the next video.